occurred, but we think it occurred in Tonga, so also in the tropics. This one we have no idea yet of the source of this eruption, and I will focus on this one, which get the highest peak of the temperature anomaly. So we made a paper about the climate response to this eruption a few years ago. So you can have much more details in this paper. So among the climate disturbance, we can notice bad harvest, grape harvest delayed in France. If you have a look on this graph, it's the grape harvest, and the date of grape harvest. Here, it's the grape harvest date, but it's the number of days since the beginning of the year. That means that in this case, for example, the grape harvest occurred 250 days from the 1st January. So you have to calculate. But anyway, the most important is that when the date of harvest is in the lower part of this graph, that means that the harvest occurred very, very late during the year. And if you look at this, the latest harvest that are represented here occurred the year after the eruption. In this case, if I'm not wrong, the harvest occurred in November, the beginning of November. Usually in France, the grape harvest occurs in September. So it was almost 2 months delayed. So that means that the climate impact was very, very strong in this case. So this is in French, so I will pass to the next slide, but it's almost the same. So the harvest were all delayed or very bad. So that triggered in Europe the year after the eruption, some disasters in Europe, a lot of disasters. Thousands of skeletons were found in London and dated at this time. So due to a big epidemic that followed the bad harvest and the famine. So there are some papers about that. Our tropical volcano devastated medieval London, and it was the same in France, and it was the same almost everywhere in Europe. This is a map that is a kind of summary of the environmental problems that were noticed at this time for the year 1258. So if you look at the regions, there are some summers referred as abnormally cold, heavy precipitation, inundation, bad harvest, high price, famine, and so on, dry fog. So a lot of problems. And what is specific after a big volcanic eruption is that the climate, the weather anomalies are not located in only one specific area, but almost everywhere in Europe, especially in Western Europe. The cold temperature are noticed during the summers, are noticed in the west part of Europe, but in the east part it's a bit different. Usually it's warmer than usual. So there were also weather anomalies noticed in Japan here, and after volcanic eruption, a big volcanic eruption, the response in West France, in West Europe, and in Japan are quite similar. So in Kyoto, for example, we found there are some sources that the paddies and garden, various products have been damaged and destroyed because of the bad weather. There are also some growing representation of this hungry ghost during at this time, just following this eruption because of the famine and so on. So this very big eruption was very important to study, but at that time we didn't know what was the source of this eruption. So that was one of our tasks to look for this eruption, for the source of this eruption, because when you don't know the source of the eruption, you can not go too far in the study of environmental impacts or climate impacts of this eruption, because the climate modelers, the paleoclimate modelers, need some data on this eruption, the column height and the latitude of the volcano and so on. So they need information about this eruption, but without knowing the source, you cannot do anything. So what are the indicators to track the source of this eruption or any kind of eruption, any other eruption? It's the same. I only talk about the large one. At least you need to find a Plinian eruption. Plinian, that means if you look at this graph, there are several types of eruptions. Hawaiian, so mainly lava flows like Piton La Fournaise in Réunion or Hawaii. Strombolian, Stromboli, we talked about Stromboli with Italian colleague. Subplinian eruption, a bit more explosive. But for all these eruptions, it doesn't trigger a climate impact. So in this case, it's not the most important. What is important is to study this part of the graph, Plinian and ultra-Plinian. Maybe I need to explain these two parameters. Dispersion is in square kilometers. Is the area covered by the ash or by the volcanic, if it's ash for the big eruption or explosive eruption, or the surface of the superficie of the lava flow, for example. So the superficie covered by the volcanic product, and this part fragmentation in percent is kind of the level of how to say fragmentation of the magma. That means that in the lower part it's lava flow, the magma is still like in the earth, so it's usually lava flow, and then when you reach the 100% or you're close to 100%, you have only ash from the eruption. So this is only explosive eruption, and this part effusive eruption. But it's the same magma actually, lava flow and ash from a large explosive eruption. It's the same magma, but the fragmentation is different. So a similar, another indicator is the volcanic explosivity index. So it's a bit similar. If you look for an eruption, a very big eruption that had impacts on climate, you need to focus on Plinian eruption or or more explosive, so Plinian, ultra-Plinian, or supervolcanic, supervolcanoes like Toba or Yellowstone. We can hear a lot about Yellowstone. So all these eruptions, you can see the indicators. The volume of magma, more than 1 cubic kilometer, and then up to more than 1,000 cubic kilometers. So this is the first parameter, but that is not enough to look for big eruption. So among the other indicators, you need to find a large volume of tetrafall and often pumice, because for large explosive eruption, the main product is pumice, so the very light rocks, volcanic rock. And usually after this very large eruption, a caldera is built, so the volcano collapses itself, and then you have a very wide crater, that crater due to the collapse of this volcano. For a caldera, we call caldera a crater larger than 1 kilometer diameter. So this is the formation of this caldera. So we focus our investigation in Indonesia, because in Indonesia there are a lot of calderas, poorly studied caldera, or not studied at all for some of them. There are abundant pumice. So this is official definition of pumice. So very light rock. And this pumice in Indonesia, or like everywhere in the world, are exploited. So there are a lot of quarries in Indonesia. This one in West Java, but almost in everywhere when a large volume of pumice is produced, they have an economical value, so they are exploited. So that helps a lot for the researchers, because we have nice outcrops, and sometimes within the outcrops we have some charcoal or some trunks, tree trunks. So for dating, it's very easy. So we finally find the source of this big eruption that occurred in Lombok Island. Lombok is not very famous for some of you, maybe, except the Indonesian colleagues. But maybe you know more about Bali. Bali is famous everywhere in the world. Bali is just here, close to Lombok. It's the next island. And this one is Sumbawa, the site of the Tambora eruption. This one. So in Lombok, you have all the parameters that are due to find a large volcanic eruption are all found here. A large caldera that you can see here, 6 kilometers wide. So 6 kilometers is very big for a caldera. That means the eruption was very powerful. There were several stages, and the main volcanic stages were already published. All volcanism for this volcano, this one, and this spot. The Sembalun caldera is in this area, and the Rinjani volcanic complex, all this part, Rinjani volcano is this one, and with a large volcanic eruption that was already done. So what is very interesting when we study a volcanic eruption, which is not too old, that means when the eruption occurred during the historical time, you can find some written sources which can be either real historical account or kind of legend, because usually we don't know exactly if the part of reality or the part of myth. So it's in Indonesia, the local legends are called babat, but it's not really legends. Or in the babats you can find myths, but also actual fact that historical fact that occurred in the past. So in Lombok, the babat are written in Old Javanese, almost Old Javanese language. It's a bit different. They are written on palm leaves that we call lontar. Lontar is this kind of books. It's a kind of book, old book, so written on palm leaves. And in the Babat Lombok, this one was translated from the Sanskrit to the Javanese, the present Javanese language. So, and then we needed to translate again in Bahasa Indonesia, in Indonesian, and then in English. So that was a long way. But the thing which is very interesting is that this eruption was described. We have the proof that the eruption that is described in this book is the same one. We found another babat which is called Babat Sumum more recently, and there are also some interesting sentences about a big volcanic eruption. And there are other babat, but only a few of them were studied. So there are still a lot to be discovered. So this is the overall methodology to study past volcanic eruption. So it mixes together some different approaches. Volcanology, of course, geomorphology, and social science. Social sciences. So, when you have some description of volcanic eruption, you can work on human settlements. So, archaeology is also involved, not in this study, but maybe in the future. For sure, in the future, some archaeological sites will be discovered in Lombok, but not yet. It's just the beginning. So we worked on the caldera, and we reconstruct by using a numerical model. We calculated the pre-caldera volume. We reconstructed Paleo Valley, Paleo Shore, and so on. And for the volcanological study, it's a usual volcanological study to reconstruct the isopack and isoplate map. Isopack is the distribution of the thickness of the deposit, and isoplate is the size of the deposit, so the maximum size of the deposit. And it is this one, the isoplate map, is very useful to reconstruct the column height of the eruption. So to present the volcanic processes and landforms due to this eruption, I chose to start from to compare the content of the babat with the science, with the field data. Because the title, you remember, the title of this presentation is interdisciplinary study. So the idea is to use field data, but also written sources from the babat. So there is a sentence in the Babat Lombok which states large blocks and soil torn pumice. The word pumice is written in Japanese, and sand fell in the middle of the line. So fell, that means it's related to ashfall and to tetrafall. So these tetrafall are found in the deposit almost everywhere in Lombok, but not only Lombok, also in Bali and even in Java and in Sumbawa. So we counted 3 main Plinian tetrafall units, which are quite easy to find in the field because pumice is white, and the other rocks are weathered, so brown usually. So you can see a layer, very easy to find the several layers in the field. So we got the three main phases for this eruption. Rain and fire fell in the ground and burned Talkuwang. Talkuwang is the former name was Taliwang. Taliwang is here in Sumbawa. We found this sentence in the Matsue, another Baba. So the eruption was described by people from Sumbawa that were located in Sumbawa. So as you can see, the isopac map, the distribution of this is the thickness of the deposit in centimeters. So here, 2 centimeters, 2 centimeters in West Java, and up to almost 20 centimeters in Bali. So that means that all Lombok, Bali, West Sumbawa, and the east part of Java were totally covered by the volcanic deposit from this eruption. So one sentence, very interesting sentence in the Babad, found in the Babad Lombok, is that this one, Mount Rinjani avalanche and Mount Samaras collapse. That was very, very important because Mount Rinjani is this volcano. It's a very high volcano. One of the highest peak in Indonesia, 3,700, more than 3,700 meters above sea level. So this volcano is still here, and every summer a lot of thousands of tourists hike this volcano up to the top. But what is interesting is that now here you have a very nice lake, called Segara Anak, with a new cone, Barojari cone, a new volcano that is still growing, and a lot of small eruption occurred every 2 or 3 years. And but what is written in the Babad, Mount Samaras collapsed. So that means that in this area there was another volcano, and that we reconstructed the former topography. There were 2 twin volcanoes, Mount Rinjani, that is still here, and Mount Samaras, the one which collapsed. And the name Samaras comes from the Babad Lombok. Sometimes some volcanologists, some colleagues ask me, why did you call this volcano Mount Samaras? It's Rinjani, but it's not Rinjani actually, because there were 2 different volcanoes in the same volcanic complex for sure, but the volcanoes have different names. So I just got the name, the actual name of the volcano, Mount Samaras. We reconstructed the total volume through this numerical modeling. We calculated the volume of material on it. It's not almost, but more than 40 cubic kilometers. So this is a very large eruption, that it's at the limit of the ultra-Plinian eruption. So Here in this area, you can see that a large slope failure occurred. It's maybe easier to see here. And this sector failure, the flank of this volcano, the Rinjani volcano, collapsed at the time of this eruption because it's also written in the Mount Rinjani avalanche. So the chronology is the collapse of the Samaras volcano first, and then because of this collapse, part of the Mount Rinjani avalanche and the deposits are for sure within the lake. So it's also written in Babad Lombok, large flows of debris accompanied by the noise coming from boulders. So it refers for sure to dense pyroclastic density currents, PDCs, which is now we use in volcanology this kind of this word, dense pyroclastic density currents, PDC, instead of volcanic how to say pyroclastic flow or pyroclastic surge, but it's the same. Pyroclastic flow, it's the dense part of pyroclastic density currents, or pyroclastic surge is the more light part, so mainly small fragments. So if you look at the map of Lombok, this is the distribution of the PDCs, and it covers a great part of Lombok, all the northern part, and also the southeast and southwest part of Lombok, up to Mataram. Mataram is the capital city of Lombok, and is located just in this area. And the second largest city is Selong, and Selong is also located just here. So if we look at the thickness of the deposit, we can find here, for example, 50 meters of pumice from the bottom to the top, 50 meters. Here there are some quarries, this 25 meters, a big cliff, a large cliff here, a very famous 35 meters. So they are very thick deposit. So the dilute pumice-rich PDCs, so what we call pyroclastic surges, were also described by the Matsue design. It's written, burning winds coming from the sea burn people in Taiwan. So that means that the burning winds, it's typical description of these pyroclastic surges that cross the sea, they cross the Alas Strait and reach Kaliurang. And it's a similar process that was described for the Krakatoa